One of the fundamentals in applying calculus to solving problems that occur in other parts of real life, calculus is real life too, but is the tangent line approximation. And it's quite fundamental, and so it's best to start with this. So what I've done here is I've drawn in black a graph of y equals f of x, and I've got a couple of tangent lines, and the tangent line, it hits at a point, it only touches the curve once near that point. Some of these touch at other places, and it has a slope. And so what you have with this tangent line is a point and a slope. The big idea is that the tangent line stays close to the graph if you don't go too far away. I mean, here it's too far away, or here it's too far away. But if you stay very, very close to the point that you know, then the tangent line is a good approximation to the actual graph. This is how calculus is used. This is like one of the top three in what computers are used for in the world. And so there's the deal. So you've got a point and a slope, and let me remind you about the point slope form for a line. This is the most important form in calculus. So if you have the point is AB and the slope is M, I don't know why slope is M, but it's always been called M. So what you have is, you just take the data that you're given, the point and the slope, and you rearrange it, and now this is an equation for the line. The thing is, in any of these, we have the point. Where are we going to get the slope? Calculus gives you a good way to get the slope, but this tangent line approximation isn't just calculus. It's really common sense. Calculus sharpens it up so that you can get an exact slope, but I hate to sound old, but when I was in high school, we would just, before we took calculus, like in physics lab, we would just eyeball this, and we'd say, oh, that slope's about 2, and that would give us an estimate for the slope, which we could then use. And so that's a good way to use things. I do have to say something about this tangent line approximation, and this is with regard to the basic function. What you've got here is the basic shape of a line, y equals x. So, and I've said before, and I'll say again, that that's all you need to know about a line, because what we've got here is that the line has been shifted to the point A comma B, and so that's one of the standard operations that you can do with any formula, any curve, any graph. So now we're at A comma B, but we've also shifted the slope. And the way we've done that is with this m. So an m factor in the x direction means that you shrink by a factor of m. And let me show you how that gives you the slope. What used to be 1, 1, if you look at y equals mx, is now the point 0, 0, and now we've shrunk everything by 1. So on y equals x, you go through the point 1, 1. But in y equals mx, you go through the point 1 over m. That's the shrinking in the x direction 1. And if you look at that, the rise is 1. The slope, the run is 1 over m, and so the slope is m. So this point slope form fits in with the way that we transform basic functions, and it's also very useful, because if you have the point and you have the slope, you're just putting the data in the right slots. Okay. So slopes they're really, if you're going to be eyeballing them, there's the obvious ones. The horizontal is slope 0. Vertical is slope infinity. Let me label this as being slopes. But some of the other slopes that you can see you can just actually see them. So slope 1 is, I've done this in green, and slope a half, well, you only go up half as far. So there's there's slope a half, and slope 2, as you go up twice as far, this is going to go way up into the stratosphere, and so there's slope 2. So you can look at a line and say, oh yeah, that's, I don't know, 3, 4. It's actually quite useful just to have a good estimate, and we'll practice with that in a second. And so that is enough. Calculus gives you the exact slope. It's going to take us a while to get to that. But even the eyeballed slope is something that can be very, very helpful. Okay, well, let me throw in one more slope here that because let's look at the negatives. So so let me just throw in this minus a half. 1 is 45 degrees, 2 is steep, a half is shallow, and things go on from there. Okay, so what we're going to do is we're going to take a graph, and we're going to pick a point, and we're going to eyeball the tangent line, and then use that to do the tangent line approximation. The basic formula for the tangent line approximation is this: if m is the slope of the tangent, then what we do is replace the actual curve with the tangent line, because that's easy to compute with. And so what we're going to say is that y minus b, well, I'm sorry, I should say ab is the known point. So here's the situation. We've got a known point and an idea of the slope. Calculus gives us the exact slope. For now, we're just going to estimate it, and it's still going to be useful anyway. So now the tangent line approximation says this, that y being a point on the curve that's going to be hard to compute, what we're replacing with is the point on the tangent line. So x minus a needs to be small here, and we're saying that the difference between y and b is approximately the slope times x minus a. And let me make a note that this is when x minus a is small. Small varies from context to context, so I can't give you a number for small. It depends. So you have to use some judgment there. So this is the basic thing that we're talking about, and this tangent line approximation, and it's one of the foundations for solving all kinds of problems. So let me label this as such. So let me show you this in action with something that works out pretty well. And again, it's kind of a basic function thing. So let me take the graph of y equals x squared, and I've drawn a pretty, it's a pretty good parabola. I mean, I could do better. You could probably do better. But there it is. That's a parabola. It's one of our basic shapes. And the anchor point is 0, 0, and we haven't moved it at all. And I want to see what's going on at the point 3, 9. So that's our known point. Like if we were taking square root of 9 is 3 anyway. So now this is something, squaring is something that we can do, but this basic principle applies to things that we can't do so easily. So I've got this, I'm going to say my scale isn't all that good, but we'll just kind of adjust for that. My x is too broad. I mean, this vertical piece should be 3 times this horizontal piece, because 9 is 3 times 3. But we'll just go with that. And I'm going to draw in a line that's not the tangent line. So I'm going to draw in this line. This is not the tangent. So I'm going to label it as not tangent. So you might recall from pre-calculus that's called a secant. And the reason I've done this is that that line has slope 3, 9 over 3. So so that means that the tangent line, let me draw this, let me show you what I've done here. The tangent line, which I'm now going to draw in, has slope bigger than 3. Bigger than is often more important in calculus than the actual how much it's bigger than. It's just it's bigger than. So the green is the secant. We know that that slope is 3 because it goes through 0, 0, and 3, 9. And the red is the tangent. I've exaggerated a little bit, but I've been known to do that for dramatic effect. It's steeper. How much steeper? I don't know. I'm going to guess. I'm sorry, I know calculus, so I know exactly what the slope is, and pretty soon you will know exactly what the slope is. But let's just take this guess that the slope is 5. It's not. It's close. 5 is bigger than 3, so that's an educated guess. It's based on an idea of knowing that the slope is steeper than some other slope. So we're going to guess m equals 5. And so the tangent line equation is y minus 9 equals 5 times, well, whatever this line is. It's close to the tangent line, x minus 3. So this is the line. And so now we're going to say the squares. So y minus 9 is approximately 5 times x minus 3. So there's the approximation. It's not exact. It's an approximation. I said from the get-go it's going to be an approximation. It's an approximation, and then let's actually see how good it is. So if x is 3.1, this is saying that y minus 9 is approximately, so this would be 3.1 squared, is approximately 5 times 0.1. So y is approximately 9.5. And in fact, 3.1 squared is, I just had it. It's sideways. Oh, I didn't write it down, sorry. 3.1 squared is, I think it's 9.61. You can multiply it out or get a calculator. So we come up with 9.5, and the actual value is 9.61. It's actually, that's like within 10%. So this could be a pretty good estimate. And so there's the deal. And it also works the other way. If x is 2.9, then x minus 3 is minus 0.1. So we're going to say that y minus 9 is approximately minus 0.5. And so y is approximately 8.5. That's not bad. Now, the thing is with squares, we could have just done this. But for a lot of other things, it's quite useful to approximate it like this. So here's the tangent line approximation. We say, oh, this curvy curve, it's hard to calculate with. So we're going to replace it with the tangent line. The tangent line has a point that we know, and it has a slope that we're going to guess. In a little bit of time, you're going to be able to calculate a lot of these slopes exactly using calculus. But for the moment, you still have a useful idea about how to approximate functions, and often this is good enough for doing whatever other problem it is that you're trying to solve. So there's the tangent line approximation, and it's something that gets used. See, this is a 13.5-minute video. The world has used this 13.5 bazillion times while we made the video.